All right, let's jump right in. Picture this. We're in the mythical kingdom of AlgoLand, a place where everything, especially numbers, lives in perfect, sorted order. We're going to follow two of our heroes, Arya and Dev, who are on a quest from the king, a quest that's about to reveal one of the most elegant and powerful algorithms ever created. And right out of the gate, you see the problem. Arya's staring at this huge scroll, 10,000 numbers, and the king wants an answer, like yesterday. Just thinking about checking them one by one feels totally impossible. This is the perfect setup for a much, much smarter way to solve the problem. So we're right there with Arya on this quest. Her first instinct, just start at the top and check every single number, is what we call a linear search. It's simple, sure, but with 10,000 numbers, that's painfully slow. No, she's gonna need a better way, a secret weapon. And here you can see the two paths she could take. On one side, you've got the slow path, the brute force way. But on the other, that's the fast path Dev is about to show her. A strategy where you cut the problem in half with every single step. Believe me, it is a complete game changer. And that right there, that's the heart of it. The secret isn't about working harder. It's about a legendary strategy called divide and conquer. The entire goal is to work smarter by eliminating massive chunks of possibilities with every single move. Absolutely no wasted effort. Dev's analogy here is just perfect. Think about it. If you're looking for a book in the M section, you're not going to start at A, are you? Of course not. You intuitively jump straight to the middle of the library. You look around, you figure out if you've gone too far or not far enough, and boom, in one move, you've just eliminated half the entire library. This is exactly how binary search thinks. Okay, the library idea is great for getting the concept down, but let's see how this magic actually works with numbers. We're going to take a tiny piece of Arya's scroll and walk through this whole thing, step by step. So here's our list, 11 numbers, all nicely sorted, and our mission is to find the number 73. Now, a linear search would start with 10, then 20, then 30. You get the idea. But we're not doing that. We're going to use Dave's method. So here's the crucial first move. We don't start at the beginning. We jump straight to the middle element, which is 50. Then we ask a really simple question. Is our target, 73, bigger than 50? Yes, it is. And because the list is sorted, we know for a fact that 73 can't possibly be anywhere on the left side. Just like that, bam, half the list is gone. Now our world is so much smaller. We only have to worry about the right half of the list. And what do? The exact same thing. We find the middle of this new, smaller list, and what do you know? It's 73. That's our target. On just our second check, we found it. Quest complete. I mean, look at that. 2 steps. That's the punchline. The slow, a one-by-one path would have taken 8 checks to get there. The fast path took 2. That is the awesome power of cutting the problem in half. But of course, things aren't always so perfectly simple. What happens if the number isn't even there? Or what if there are duplicates of the number you're looking for? A truly great algorithm needs to be able to handle these tricky cases without breaking a sweat. And Arya asks the perfect next question. This is a super important edge case. I mean, an algorithm that just gets stuck in a loop forever when it can't find something isn't very useful, is it? There has to be a clean way to know when it's time to just stop looking. And here's the really elegant solution. The algorithm keeps track of its search area using 2 little markers, a start pointer and an end pointer. With every step, that search window gets smaller and smaller. If the number isn't in the list, that window will eventually shrink to nothing. And the algorithm knows this happens when the start pointer actually moves past the end pointer. That's the clear signal. Game over, not found. This is another great, more advanced question. What if the number 73 was in the list 3 different times? A standard binary search might land on any one of them, but what if you specifically needed to find the very first one? Well, you can actually tweak the algorithm to do this. First, you just run a normal binary search to find any match. But when you find one, you don't stop. You record its position, and then you tell the algorithm to search again, but this time only in the section to the left of your match. If you find another one, you update your record and you keep searching to the left. The very last position you record is guaranteed to be the first one. It's pretty smart. Now, this whole story about AlgoLand might feel like a fantasy, but here's the thing. This exact logic is all around us in the real world.
In fact, you have almost certainly used it, probably without even realizing what you were doing. Think about that classic number guessing game. I'm thinking of a number between 1 and 100. What's your first guess? It's not 1, right? Or 2? Heck no. You guess 50. And when your friend says too low, what just happened? You eliminated 50 numbers in one shot. Your next guess is probably 75. You are intuitively performing a binary search.
And it goes way beyond just games. Every time you open a physical dictionary, every time you search a massive database online, or even when you see autocomplete suggestions pop up as you type, you are seeing the power of binary search, or algorithms inspired by it, just efficiently tearing through huge amounts of data. So what's the mathematical secret sauce that makes this so ridiculously fast? Well, it all comes down to a concept from computer science called Big O notation, but all you really need to know is the magic phrase for binary search, log n. And this is where the difference becomes absolutely staggering. To find one item in a list of 1 million, a linear search could take, in the worst case, 1 million steps. 1 million! But binary search? It'll take a maximum of about 20. Not 20,000, 20. That isn't just faster, it's a completely different universe of efficiency. So what does log n actually mean in simple terms? It's basically just the answer to this question. How many times can I cut my list in half until I'm down to just one item? For a list with 1 million things, that answer is about 20. And here's the most incredible part. If you double the size of your list to 2 million items, it only adds one single step to your search. That's the magic. And this brings us to Arya's big takeaway. The one single requirement for binary search to work is that your data has to be sorted. But if it is, it's like having a superpower for finding exactly what you need, no matter how big the list is. And Dev's final piece of advice really sums up the whole philosophy. It's not just an algorithm, it's a powerful way of thinking about problems in general. When you're faced with something huge and overwhelming, just break it down into smaller, more manageable pieces. So, that's the thought I want to leave you with. Forget about code and numbers for a second. Think about troubleshooting a problem or trying to find some piece of information, or even just making a decision. Where in your life do you have a sorted landscape where you could apply this exact same principle of dividing and conquering to find a solution a whole lot faster?